Usually, the constraints are represented in the form of algebraic equations. We also have outputs, measurements. Systems could be linear, they could be non-linear. And in the technique which we are going to study in this course of our lectures, they are not restricted to just linear systems or non-linear systems. So we are not restricting our applications. Okay. The linear systems theory is fairly well developed, but for non-linear systems, you don't have a well developed theory except for the simple or the commonly occurring non-linear systems, and so one has to resort to simulations. That's another necessity for models and simulation of models. Well, dynamic models can be used for essentially three purposes. Can be used, one is for analysis, where you have a given input future history and initial conditions of the system, and you are going to determine the outputs. Okay. And the other application for dynamic models is in identifying a model, and that is, given an input history and an output history, you have to determine the system. But perhaps the most interesting part or the most useful part as far as engineers are concerned is synthesis of dynamic models, where given input future history and some desired output history, determining the system so that the input to it will produce the desired output. Well, it seems a bit complicated to you at this moment, but when we come to simple examples, things will become a little more clear. Now, let us have a look at dynamics and computer aided design. Analysis of dynamics, the first aspect is that analysis of dynamics is more important than statics. And if you base your designs, if you base your research work on sheer statics, there is a very good possibility that you will be misleading your research, because the effects, the dynamic effects, the consequences of dynamic behavior of physical systems is significantly different from mere static behavior. The second aspect of dynamics is that pictures and graphs are easier to understand than equations. Is it possible for us to represent using pictures and graphs rather than just deal with equations and mathematics, all the abstractions? The question is, can mathematical features of dynamics be represented pictorially in the form of pictures? Naturally, because the moment we started with physical systems with models, then we spoke of ordinary differential equations, constraints and all that. Naturally, one thinks that perhaps we are heading towards mathematics, and perhaps it may be too complicated and it may not be interesting. But then, if we can capture all this in the form of pictures, in the form of graphs, and then perhaps one can understand much better in the form of pictures rather than in the form of mere mundane mathematical equations or expressions. So can mathematical features of dynamics be represented pictorially in the form of pictures? Can this modeling methodology which we are going to study, can it be applied to any energy domain? We have seen that we have several energy domains. We have the mechanical domain, again in it we have the translational domain, the rotary domain, we have fluid domain, okay, then we have electrical domain, electromagnetic domain. So we have several energy domains, and can this modeling methodology be applied to any energy domain uniformly? Okay. If it can be applied, if we can represent our dynamics in the form of pictures, can system equations, the differential equations which we were talking of, can they be derived easily from this model, from this picture which represents the dynamics? Okay. So there are certain questions like this. And how do you simulate this model of the dynamics of a system in an easy manner? Okay. So one has to represent the physics of the system properly. Okay. One has to understand the dynamics, and so one is able to represent it in the form of pictures. And then one should be able to extract the mathematics out of it in a very systematic manner. Not only that, you are also interested in simulation. So can simulation code be derived automatically from this picture? Okay. Can a pictorial model offer insight into analysis for design and control? From the pictorial model which you are going to learn or which you are going to understand about your system, can a pictorial model offer insight into the analysis for design and control? Can you use it to determine forces, critical forces or critical moments, so that you can determine appropriate strengths? Or can you determine actuator capacities? Different aspects of physical systems. The technique which we will be studying is bond graph, and this is a unified approach to the modeling of physical system dynamics. It will attend to all these questions that we raised earlier. And in this technique, it is a unified approach, we say, because we will be in a position to handle systems across multi-energy domains. Need not be only the mechanical domain or only the chemical domain, will be able to handle across multi-energy domains. Here is an example of an electromechanical system, a simple system which is fairly commonly known among mechanical engineers and among electrical engineers, and I am sure by the end of this session of 4 days, you will also be fairly familiar with it. This is an electromechanical system. It is a system of, here you have a permanent magnet DC motor, and there is a rotor which is shown, you can see. This is a rotor and this is the disc of the rotor, and connected to this rotor are the armature brushes. Okay. So here on the commutator of this, here you have some armature brushes, and it's a winding. So this winding has an inductance and also a resistance, because there is a length of conductor and it has certain cross section. So you have both resistance as well as inductance, and we have taken this in this particular configuration. And you are also applying an potential difference across the terminals of this electrical side. And this, in this system, a current is going to flow through, okay, depending upon the parameters over here, the resistance, the inductance, and also on the load that is connected to the motor. And then, depending on that, a torque is going to be generated. And we are interested in modeling this. Right now, let's see how this will appear in the form of a graphic model. It will appear somewhat like this. Okay, this is just a part of the model. But you can see that here you have peculiar arrows, peculiar shaped arrows. These arrows are representing the transaction of power, from the flow of power from one end to another. So here on one end of this arrow you have a subsystem, and on the other end you have a subsystem. And you can see that for this arrow you have got one variable written above and one variable written below. Okay, I'll explain to you gradually what these are. Here in this case we have written, it is the potential difference across the terminals, electrical terminals, and here you have the current that is passing through the armature. Okay, and here you have got certain elements, we will call them as elements, and we will understand what these elements are. So here we have a 1, we have a R, we have other bonds, very peculiar, we call them bonds or ports. They are actually meant to carry the information of power. And you can see that this is indicating a form of transaction of energy, a form of transaction of power, and we will see how this is done. Right now I just want you to understand that it's just bookkeeping, it's just balancing, it's just showing the transaction of power among different elements. And so it is like this, that your source over here, the source of potential difference, is providing power inside. A portion of this power is going to this armature resistance, a portion of it is going to the inductance, armature inductance, and the remaining is utilized for the electromechanical coupling. Okay, so then you go towards the mechanical side, and this coupling from the electrical side to the mechanical side is also represented. And so you can see that you are able to represent two distinct domains. In fact, you have the electrical domain here and you have the mechanical domain here. So you can see that we have this domain here. This is the electrical domain, and we have the domain here which is the mechanical domain, and here you have the rotary motion of the mechanical domain. And then of course, so once you have the torque coming in on this shaft, okay, once you have the power in the mechanical domain, a portion of it is being utilized, or rather it is getting dissipated in overcoming the bearing friction, and a portion of it is being utilized for changing